Okay, 4-level systems. The third relaxation time is the lifetime between levels 3 and 4, denoted by tau g. Okay? And the range of tau g could be very large, like semiconductor, optical amplifier. Tau g is very short, in the order of nanosecond. But like urban doped fiber, the tau g could be very long, like 10 milliseconds. Okay, so it depends on the gain medium. Tau g can be very short or very long. But in any way, tau g is always much longer than tau 2-3 and the tau 4-1. The relaxation times between levels 2 and 3, 4 and 1. Okay. Finally, we have to define the stimulated emission rate S, which is shown here. Sigma g times I over U0. The physical unit is 1/second. But what are the 3 symbols? What is U0? U0 is H times nu. So you must identify it's the single photon energy, right? I is the light intensity or power density, watt per meter square, okay? And the sigma g is the effective light-matter interaction cross-sectional area. So we have to pay some attention to definition of sigma g. So what is the equivalent cross-sectional area, sigma g? A coherent photon is emitted if an incident signal photon crosses the cross-sectional area sigma g around a single ion. Okay, so this is, for example, this is a single ion. And effective cross-sectional area is defined as sigma g. So if you have a light beam and some input photon passes through this area, then there is light-matter interaction. Stimulated emission happens, new photon will be emitted. But outside this equivalent area, there is no interaction. Light just passes through, nothing happens. Okay, so this is the definition of sigma g. And a larger sigma g means stronger light-matter interaction. 这个截面积越大，就代表什么？光子很容易跟这个离子发生交互作用，造成 stimulated emission. So this is a parameter used in describing the light-matter interaction, how easy the interaction is. Okay, and it's up to material. We will talk about the impact of sigma g on laser behaviors later, but so far you can try to understand the meaning in this way. How easy the interaction can happen, how easy stimulated emission can happen, described by this equivalent cross-sectional area. And the next question is why the stimulated emission rate S is defined by sigma g times I over U0 as shown in the lecture slide. Okay? So I use this supplementary slide to justify why this definition is reasonable. Let's start with sigma g as shown in the previous slide. Sigma g means equivalent area of an ion across which an input photon can stimulate a new coherent photon. This is the definition, right? So if you multiply sigma G with light intensity I, here I clearly denote the corresponding physical units. Sigma G is a cross-sectional area, so the physical unit is meter square. I is light intensity or power density. The physical unit is watt per meter square. So after the multiplication, meter square can cancel with each other, so you got the physical quantity in the unit of watt, right? The power. But what's the power? It's the stimulated emission power contributed by a single ion, right? 好，上面这是一个 ion 的等效截面积，你把它乘上一道雷射光的强度 I 之后，乘完是什么？是一个 power， 是什么 power？ 就是一个 single ion 可以贡献的 light power。这个 light power 来自 stimulated emission. Okay? But you can imagine this is a very small number because a single ion can contribute very nominal, very weak output power only because sigma G is usually very, very small. Okay? So this is the light power due to a single ion. Then, if you further divide this power by U0, which is the single photon energy, what is the result? Check the physical unit. The numerator is a power in units of watt. The denominator is an energy in units of joule, right? What is watt over joule? The definition of watt is joule per second, right? The energy per unit time. So joule cancels with joule, so you have 1 over second, right? The physical is 1 over second. 1 over second means rate, 速率，对不对？ So the physical meaning of this calculation is the number of stimulated emission photons contributed by an ion in 1 second. Is it okay? This is power due to a single ion divided by single photon energy. So you just translate the power, joule per unit time to number of photons per unit time. 对不对？你把能量除上光一颗光子能量，不就变光子数了吗 ？Okay, so it means in 1 second, due to a single ion, how many stimulated emission photons can be generated? And this is nothing but the stimulated emission rate, as I mentioned, the percentage of electrons on level 3 drop to level 4 in 1 second. 我刚刚不是说 stimulated emission rate 物理意义是1秒钟之内有多少的电子被从高能阶第3阶驱动到低能阶，就第4阶，对不对？我说它的意义是这样，这个意义不就等于这一句话吗？ Number of stimulated emission photons must be the same as number of upper state electrons stimulated back to level 4, right? And due to a single ion and in 1 second only. Due to a single ion, so it means percentage. 百分比嘛，就一颗离子可以贡献几颗光子，这不就是百分比嘛？然后同样都是1秒钟之内。So this is the stimulated emission rate. So in these 3 steps, I think it's clear enough that you can understand why stimulated emission rate is simply sigma G times I over U0. Just use this logic. So after the introduction to four-level systems, we can try to derive laser rate equations. Okay? This is again the four-level system graph. If we focus on, say, the number density on level 1 first. We have 4 levels, so we need to write down the equations for level 1, level 2, level 3, and the level 4 respectively. Okay? But let's start with equation for level 1 only. Okay? If you look at this view graph, you know there are 2 mechanisms that can influence the number density on level 1. The first one is pump rate. If you have pump rate, level 1 will be fewer and fewer, right? Because it loses electrons by the pump. The other mechanism is relaxation from level 4 to level 1. When this happens, the number density of level 1 will increase. Okay, so you have 2 mechanisms. One, pump, reducing the number density. Second, relaxation, increasing the number density. Okay? But how to model them mathematically? So let's think about this case. Within a time interval, delta t or dt, the number density of level 1, which is denoted by the symbol N1, the physical units, it's meter cubic inverse. So you can see this is about how many electrons per unit volume on level 1. The physical meaning is like this. Okay? So the number density may decrease by this amount due to pump absorption. 所以 pump 进来的时候呢，这个 level 会损失电子 ，number density 会下降。但是到底损失了多少？损失了这么多。Is it reasonable? We know the definition of W is the percentage of transition from level 1 to level 2 in 1 second. Then the product between W and the time interval dt means the percentage, right? And the original number is here, N1. So original number times the transition percentage means the amount of transitions. And this is the amount you will lose due to pump. Okay? If this is true, then you can write down this equation. Number density at a time instant t plus dt should be the original number density N1 at time instant t minus the difference. Okay? 所以就是时间比较晚的时候的 number density 应该是比较早的 number density 再减去这一段时间的损失嘛 OK 我们已经 justify this is the loss due to the pump already analyzed here. So this equation should be true. Okay? Then just playing with the game about calculus. Okay? This one minus this one over dt, you got the left-hand side. The right-hand side, you have minus w times n1 of t only. And in calculus, you know this is the so-called difference quotient, right? 差商. Then, if dt is close to 0, this one, this difference quotient, is nothing but time derivative. First order time derivative, right? So we say n1 dot t dot means time derivative, okay? Equals minus w times n1 itself. And this is equation number 1 we have. Okay? But this equation only takes one mechanism into account, the pump. It's not complete because we have a second mechanism here, not included yet. But you can use the same strategy in deriving the equation due to the relaxation process. Very similar to this one. So in the second mechanism, N1 will increase instead of decrease by this amount due to relaxation from level 4. Okay. Let's check whether this is correct. When relaxation takes place, roughly speaking, within tau 4 the electrons on level 4 will be dumped to level 1. So this is the percentage, right? Relaxation time instant, but with an inverse here, times the time interval dt. Okay? So this is very similar to the rho W in the pump process, a rate. Okay? Tau 4 inverse is also a rate, but this is relaxation rate. This is not pump rate. The rate times time interval, you got percentage, relaxation percentage. How many percentage of electrons on level 4 is dumped to level 1 in dt? Okay? Then the original number density is N4. So the percentage times original number density, you got the change, the difference. Okay? Then you can easily arrive at a very similar differential equation. N1 dot, again, this is time derivative, equals N4 over relaxation time constant, tau 4. Okay, this is equation number 2, and you can combine equations number 1 and the number 2 together. The time derivative of N1 is actually the summation of two terms. The first one, minus Wn1 due to pump. The second, N4 over tau 4 is due to the relaxation. Okay, and pay attention to the signs. The minus sign means decreasing process. A positive sign here means increasing process. Okay? Then that's it. This is the governing equation for number density of level 1 due to two processes. Okay? Any question? If there is no question, I will skip the other cases. Okay? Equation 1 is here, and you can use the same strategy to write down the governing equations for levels 2, level 3, level 4 using the same idea. And you can see like equation 3 is more complicated because there are more processes involving, right? Let's take a look at level 3. Relaxation from level 2 to level 3 contribute to a number density increment. And the natural relaxation contributes to number density decreasing. Stimulated emission S contributes to decreasing, right? So there are more physical processes involving with number density of level 3, but the idea is the same. I will not repeat it. So you can write down equations 1, 2, 3, 4. Unfortunately, this is not enough because we all know if you have n unknown functions, you need n equations to solve them uniquely, right? 你有几个未知函数，你就需要几条方程式。How many unknown functions? Not 4, but 5. What are the 5 unknown functions? In addition to n1, n2, n3, n4, s is also unknown. S is the stimulated emission rate. Here, we have no idea about S. What is function of S? We have to solve it. So actually, we have 5 unknown functions. Then we need 5 equations, okay? But the previous idea only give us 4 equations. Fortunately, the 5th equation is very easy. Just total number density, n1 plus n2 plus n3 plus n4 must be a constant n sub g. Because all the electrons simply redistributed among these 4 states, 4 levels, right? No electrons can escape. No electrons can be generated from nothing. 所以不论你怎么分配，总和是一个常数。So this is equation number 5. So our problem has been totally defined by these 4 equations. And in theory, we can solve the system of ordinary differential equations to get all of them, n1 to n4, and s as functions of time, t. We can solve them mathematically. Okay? But of course, it's a very complicated mission to do that. I will not try to spend much effort in this direction. Okay. But that's the complete model we can use.